This is video 13 of the lecture on the design of reinforced beams. This lecture explains the optimum depth of a beam at different concrete grades. The optimum depth of a reinforced beam, denoted by d-opt, is the effective depth at a given bending moment in ULS at which the limit value of strain in the concrete and steel are reached. Optimum means full exploitation of the ultimate resistance and is therefore not necessarily the most economical depth. In fact, I found out that the economical depth of a beam is more or less 85% of the optimum depth regarding the resistance. Now consider the strain diagram. When the materials are used to their maximum capacity, then we know that the strain in the concrete is epsilon Cu2 and the strain in the steel is epsilon Ud. With the strain diagram, we have the stresses and the forces. We know that the total compressive force equals the filling coefficient times the depth of the neutral axis times the width and times FCD, and it's situated on a distance of delta Gx from the most compressed fiber. Now, a plane before loading stays a plane after loading. We use similar triangles, and we can express the depth of the neutral axis in function of the two extreme strains in concrete and steel. Now we got a second equation, which is the rotation equilibrium at a tensile reinforcement. It is around this point. We take a rotation equilibrium, which is nothing more or nothing less than the total compressive force multiplied by its lever arm, which is d minus delta Gx. So we got the compressive force times the lever arm. In this formula, we can substitute x and we can find d, because that's what we wanted to do. We wanted to find the optimum depth d when epsilon Cu2 and epsilon Ud is reached. If we do that, then this is the general expression of an optimum depth under simple bending of a reinforced beam with rectangular section. Z equals this expression here. This is valid for all concrete grades. Now let's give an example. What is now the optimum depth of a section in a concrete grade C90 105? Then in Eurocode 2 on table 3.1 you have the different values of the strains for the concrete, and then we can see in this table that epsilon CO2, which we want for C90, it's 2.6 promille, not 3.5 as for C50-60, but 2.6. Epsilon UD, we've taken 10 promille by convention. Epsilon CO2 is 2.6 that we found in the table. What we have to do is to calculate the filling coefficient. I left out the width of the section. So the filling coefficient equals it's just the integral, and you see here the stress in function of the strain, that this value changed. It changed because this is the proper value for C90 concrete grade. It's also, you can find this number n, that's number n, in the table that we have just shown now, table 3.1. So if you calculate the integral, you find this value. So now we know, see, the filling coefficient is 7/12. We also have to calculate the lever arm, no, not the lever arm, but the point of gravity, delta G. We do that by means of an equilibrium, a rotation equilibrium, and we do exactly the same I've seen in the previous lessons. This is the stress, and this is the coordinate S, and we make an integration between 0 and x is the depth of the neutral axis. From this we can derive delta G, and delta G equals 6/17. Now we have, that's all the information for C90. That's all the information we need to use the formulas that we just put forward. And if we calculate Z, we find 30.3, and if we calculate the optimum, we have 2.99 square root of the bending moment divided by the width and FCD. Take care of the units. The most simple way to approach this equation is, if you fill in the bending moment, you just fill in the bending moment in kilonewton meter and multiply by 10 to the power 6, B in millimeters, FCD in megapascal. At that moment, your answer is an answer in millimeters. So just take care of the units when using this formula. Consider this table. These are different concrete grades, smaller than C50-60 up till the high strength concrete C90-105. These are the filling coefficients, the point of gravity, delta G, the epsilon CO2, you see that this is declining. It gets less and less ductile when you have a high strength concrete. And then in the formula of the optimum, the coefficient alpha, we know already from previous lessons too that for C50-60 it's 2.31. And you will see this that this number changes with increasing concrete quality. But something terrible is wrong about this table. This is an increasing concrete quality, and it gives the impression that you need an increasing optimum depth. That's not logic. So what's wrong? Well, what's wrong is that FCD is still in here. So we should use the proper value for FCD with those values of the concrete grade. If we do that, then we have a new formula. I call it now beta, just took FCD out. And then with this formula, this is independent of the concrete grade, the formula itself. So now you will see that the coefficient beta, which is of course dependent of the concrete grade, the beta, you will see now that this is the result that you expect, which is logic. The stronger the concrete, the less your the optimum will be. The optimum of a beam subjected to bending at a concrete grade smaller than C50-60 is given by this formula. We use this formula to determine the needed depth of a beam, so it is a design problem. See you at next lecture.